leadership. It is his devout wish that America become one of many nations influencing the world indirectly or not influencing it at all, rather than the indispensable nation, as Madeleine Albright.
All right, we're looking at conservation of energy here. We've already discussed the concept of total mechanical energy, which, as you can see, is defined as kinetic plus potential energy. Kinetic energy is always given by the same formula, 1/2 mv squared. Whereas the potential energy depends upon the particular force that we're talking about. Simple statement of conservation of energy simply means that the before calculation of the total mechanical energy, K plus U, must equal the after calculation of the kinetic plus potential energy. So in doing problems, all we need to really figure out is what is the potential energy at the condition at the end of the problem, and what is the kinetic energy in both the before and after, as well as the potential energy. This principle actually arrives in prior times as a result of investigations into thermal dynamics, and then became apparent that it was also applicable to mechanical situations. Now, sometimes we find that the energy before and after is not equal, and therefore does not equal 0. In such a situation, we have to look to see, are we losing energy due to some non-conservative force? And the non-conservative force in this case would be, in our calculations, would be friction. You can understand that because you realize that if you push an object across a surface against friction, it does matter the path you take. For instance, take up here, let's make this a crate, and we're going to move that crate from, and we're looking down on the top of the table, we're going to move that crate from this position straight across to the final position, and we'll allow there to be friction. And you could calculate the work that you would do by multiplying the friction that you have to overcome times the distance d. What if we took a second path, and we took the box up here and we brought it around, and then we brought it back, and we ended at the same point? Would the amount of work that you do be the same or different? And as you know, your common sense tells you there would be more work involved in undergoing the second path path 2 because you had to cover a larger distance d against a constant frictional force. So what we find is that friction, when involved with work, is a non-conservative force, and it's path dependent. I don't know if I can write that up here successfully, but let's try. Path dependent. I won't write out the full dependent word. Path dependent. So if the particular force that the work is being done against is path dependent, then you're not going to find that the energy is conserved, because it will matter where you start. It won't be exactly where you start and where you end that matters. It will matter what is the pathway you follow. So we still have the concept of initial and final kinetic energy, and those are conserved as long as we're not dealing with any path-dependent forces such as friction. So that's why we say here a non-conservative force consumes energy. And we talk about the work done against that non-conservative force. And then again, we can illustrate that very simply. Let's take an example of, we have a box here, and the box is on a level surface, mass m, moving with a velocity, let's say it's moving at 10 meters per second. And there's friction. Let's give the floor a coefficient of friction of, say, 0.3. Okay. After a certain distance, the box will come to rest. Obviously, it has a velocity of 0 at that point. And then let's analyze the mechanical energy both at the beginning and at the end. At the beginning, what do we have here? We have kinetic energy, and let's give the box a mass of 1. That makes it easy to calculate. So kinetic energy is 1/2 mv squared, so that's 1/2 of 1 times 10 squared is 100. So altogether that means 50, isn't it? 50 joules of kinetic energy. That's K0. And since we're on a level surface, we have no potential energy. So we'll call that U equals 0. So our total mechanical energy at the beginning of this problem is E0, 50 joules. Okay. Now go to the end of the problem. What is the total mechanical energy down here? It's not moving, and of course it's still on the same level surface. So it means we have 0 joules of mechanical energy at the end. So notice what happened. We lost 50 joules in order to do work against friction. And that's what we mean by a non-conservative force. It's not conserving the energy, it's eating up the energy. And so that when we look at the conservation of energy principle and says, is E0 equal to E final? The answer would be no. E0 is not equal to E final because there was an external force acting that dissipated that energy in the form of doing work against friction. Another way to look at the rate at which we're doing work is to talk about the concept of power. We use a symbol, whoops, Didn't get any ink there. Use the symbol P for power, and it's defined as work over time. You can see that the units on work are joules, or the Newton meter. Right? Let's define work up here again. Work is force times distance, which has the units of Newton times meter, which of course is also equivalent to a joule. So we have the units of joules for work and seconds for time, and we define that unit as the watt unit. Okay? So this is a unit. This is not a symbol for work. Okay. Let's emphasize that. This equation is the definition of power. Notice as well, if we put in the definition of work in our equation for definition of power, replacing W with F times D, we can also write power as a product of force times velocity. That's sort of an alternate definition of power. And the importance of understanding power is so that we can evaluate mechanical systems on the basis of efficiency, which is defined as what you get out versus what you put in, whether it's work out versus work in, or power out versus power in. Well, let's look at some examples of mechanical systems. Here we see a skater on a parabolic ramp, and if we resume the program, see the skater going back and forth from a particular height on one side to that height on the other side. Let's ask to see the energy as a function of position. Drag that up here. The thermal energy is just simply, in this case, we're going to assume there's no loss of energy due to heat or friction. So notice the red line is 0. The total energy, which is the sum of the kinetic plus potential, is also constant up here at 4,000. And you'll notice that as the skater passes through the bottom of the arc, the kinetic energy in green reaches its maximum value, and then reaches 0. Kinetic energy reaches 0 at the extreme points here and over here. Right? So the kinetic energy is going from 0 to a maximum in the middle and 0 again. At the same time, the potential energy is doing exactly the reverse, going from a maximum up here to a minimum and to a maximum. So here we are at the top, and come down and back up. Between the green line and the blue line, they add up to a constant value given by the total energy. Because we don't have any friction, we're not doing any work against friction, we're not losing any energy. Let's look at an example of conservation.
Been brushing and flossing your teeth, keeping them nice and healthy, huh? Not going to do much good if this 14-pound ball comes crashing through them, yeah? Watch this. I want to show you a nice physics demo. the ball doesn't smash my teeth. How come? How come? Because of a very important conservation principle called conservation of energy in physics, which states this: take some energy to lift the ball, yeah? Now it has energy of position. Call that potential energy. I let go, it turns into energy of motion, kinetic, back to potential, kinetic, motion, but no more potential energy afterwards than that which I start with. Try this sometime. Give the ball a little push. You better move your head. You know why? Because you gave it some energy in addition to the potential energy, and it will come higher.
All right, let's look at a particular Mastering Physics problem on your Chapter 5 assignment. This problem shows a runner approaching a sled at the top of a hill. You're told that the sled is 20 kilograms, the hill is 20 degrees, and a 50-meter long ice-covered ramp. At the bottom of the ramp there's a spring. The spring constant is 2,000 newtons per meter. We're told that the runner can run a maximum of 12 meters per second. So we approach this problem from the standpoint of energy. Okay. And look at the total energy up here at the beginning of the problem. What do we have? Well, the runner has kinetic energy. Let's call that K0R. And the runner has potential energy, U0R. But the sled also has potential energy because it's up relative to the ground, so we need to add potential energy of the sled, U sub S. And the sled is not moving, so it doesn't have any kinetic energy. So we could calculate those three things because we know that the runner's mass is 40 kilograms. She's moving at 12 meters per second. We know the mass of the sled is 20 kilograms. So when we calculate mg/y, potential energy for the sled and for the runner, we've got their mass, we've got g, and y. Well, y is the height of this triangle, and we know that the hypotenuse of that triangle is 50. So we can determine y for both the runner and the sled. So it looks like we have everything to find the total mechanical energy at the top. Now let's come down to the bottom. Down here, the spring gets compressed. Let's draw a line and show that spring is compressed against the stop. And what kind of energy does the spring have in that state? Well, it has potential energy, doesn't it? Calculation of potential energy is 1/2 K x squared. And that's what we're looking for. The problem up here says find x. Find x. Okay, so down here at the bottom, with the sled and the runner momentarily stopped against the spring, so they have no kinetic energy. Kinetic energy at the bottom is 0. The gravitational potential energy at the bottom is 0, and the only energy that we have is stored in spring potential energy. So we're going to set our calculation of total mechanical energy at the top equal to the total mechanical energy at the bottom. And the only thing that would be left was to find x. Okay? All right. Okay, that concludes this little video demonstration of conservation of energy. We'll have a, pardon me.